All right. Said we're live.
This meeting is being recorded.
And there we go. Okay, everyone, thanks for joining us today for EPSP Connects. We're going to have a science talk from Dr. Rachel Glade. I'm Kevin Pierce. I'm a postdoc at the University of Oslo, and I'm co-hosting with Maddie Kelly from Arizona State. Maddie will be fielding questions at the end, and just to explain quickly the question format, as the talk progresses, you can type your questions in the chat, and Maddie will read those out when we get to the end of the talk. So Rachel Glade is an assistant professor at the Department of Earth and Environmental Sciences at the University of Rochester in New York. She's the leader of the DRIP Lab, and the DRIP Lab studies how sediment dynamics influence the evolution of Earth's surface. So today we'll hear about her ongoing research on Arctic landscape instabilities and how we can relate these, or how she has formulated relations between these with fluid dynamics instabilities. So without further ado, let's hear from Rachel, and I hope we get some interesting questions for the end of the talk.
Great, thank you so much, Kevin. Thank you for inviting me to be here today. I'm really excited to share this work with everybody. The work I'll be talking about was sort of originated at Los Alamos National Laboratory in collaboration with some scientists from Carleton University and MIT. It was part of the NG Arctic project. This is a large DOE-funded project that aims to understand how climate will impact landscapes in the Arctic. And then now we're continuing this in our lab at the University of Rochester. So if you look at the image in the background here, if I didn't have a scale bar, you might think it's like fish scales, or I've heard people think it's a microscopic image of some kind of texture, but these are actually large scale landscape patterns in Norway, found on sort of the islands and just off the coast of northern Norway. And in this image, they have a wavelength of, let's say, tens of meters. And these things are known as solifluction lobes. So they're common patterns that you see in Arctic landscapes on Earth and also in Antarctica. So, again, here are some different images from across the Earth. If anyone knows where the bottom right one is, I could not find the actual location. There's a lot of images on Google, but no reference. But these patterns are really striking. You can see them from certain satellite imagery and certainly from aerial imagery. And, it kind of looks like the landscape is melting in a way, or the soil is just sort of flowing down slope. And some work on these features has shown that they result from a process known as solifluction, which is sort of a two-part geomorphic sediment transport process. So when you have soil in a cold place, if it's cold enough, during part of the year, any water that is existing in the soil pores will freeze. And when that happens, you get sort of an instability that occurs known as ice lensing. So in addition to the fact that ice volumetrically expands, ice is less dense than water, that poofs up the soil a little bit, but the actual main component of frost heave is this formation of ice lenses, where liquid water that's super cooled in the soil will migrate through the pore space and form these lenses of ice that cause the soil to loft upwards. Then in the spring, when the ice thaws, that soil settles vertically and has a net downslope motion. As you can see in the lower left figure here, these are displacement profiles from experiments. So you have this vertical frost heave, some vertical settling, and then something known as gelifluction, in which the partially or fully saturated soil kind of flows down slope like a fluid. And as you can probably guess, this is a very complex process. And people have done many field studies and some experimental studies, but we really don't have a great idea of exactly how these processes form these patterns. But we do know that in general, this solifluction results in sort of these drip-like patterns on hill slopes. In the lower right here, you can see a drone image of a solifluction lobe in Colorado. It is certainly lobate, as you can see from this picture. And this process results in these instabilities where the soil kind of forms these discrete lobes that can be rather steep on the downslope side. So this process, even though in the upper right image here, it kind of looks like, it almost looks like water rushing down a window or something. This process is incredibly slow. So the velocities of these solifluction lobes are millimeters to centimeters per year. And we know that because people have done, drone studies, DGPS studies, also just putting, rods in the ground and digging them up 10 years later, we can quantify the velocity of these lobes. And in general, the depth of motion that forms these features is, a meter or less. So they exist sort of on the skin of the soil surface. So why might we care about these? These are sort of a characteristic feature of these Arctic landscapes where climate change is already rapidly causing degradation of the landscape. So these images are all from Alaska, and you can see that solifluction and frost heave processes really cause a lot of damage to infrastructure and the environment. So better understanding how these things work is, not only just an interesting question from a sort of pattern formation standpoint, but it is also very important in our efforts to try to predict how climate change is going to alter landscapes on Earth. Also in this talk, I'm going to not only talk about Earth, but other planets as well. So some recent work has found very similar lobate features on Mars, particularly in crater walls. They're a similar scale, they're a little bit bigger. So in the image on the left here, you can see the wavelengths are tens to 100 meters. But they tend to look rather similar to these solifluction lobes on Earth. And the interesting idea here is that if these features on Mars are in fact solifluction lobes, that has some pretty sweeping implications for past and maybe even present climate on Mars. We don't know if these are active right now on Mars, but they do tend to be found in the high and low latitudes, pointing towards some kind of climate control. So if these things require ice and water to form, and we see them on Mars, that's pretty cool, right? That has some really interesting implications for the presence of liquid water on Mars and what the climate might have been in the past. So in this talk, I'm going to walk you through our efforts to start answering three main questions. In thinking about how these features work both on Earth and other planets, first, I would argue we really need to understand how do they physically form? What causes the formation of these instabilities in landscapes? And to do that, I'm going to walk you through a theoretical analysis that we've done, kind of as a first step toward trying to understand what are the necessary ingredients for these things to form. I'm also going to talk about how climate affects solifluction. So there's a, kind of an obvious idea that climate has something to do with solifluction, right? We see these patterns really only in cold places on Earth. They're associated with these freeze-thaw processes, but we don't really have a good idea of how certain climate regimes or temperature cycles actually affect their morphology. So we'll talk about that. And then finally, I'll show some very new work that's coming out of our lab, looking at Martian lobes from high-rise imagery to try to understand, are they quantitatively similar to solifluction lobes on Earth, or are they just kind of a different sort of lobate feature that look similar? So first, I want to try to figure out, how do solifluction lobes form? We know they exist. We know they're associated with freeze-thaw, but we don't really have any sort of, quantitative or even conceptual model of what causes them to form. So in this kind of crazy image here, right now I haven't labeled any of the pictures, but I want you to just look for a minute and think about, what we're looking at. There's kind of a spoiler, this larger image on the bottom I just showed you, those are solifluction lobes in Norway. And, I guess I showed you this one too. So, these two are solifluction lobes, but what are the other images? So the other images here are potential solifluction lobes on Mars, water flowing down a window. I've shown these images to many people, and a lot of people think the water flowing down a window was solifluction lobes with a road cutting across. It's very hard to tell the scale in some of these images. Here's honey dripping down a plate or something. And then in the lower right here is one of the first experiments on fluid fingering instabilities done by Huppert in 1982. So this is oil flowing down a plane, and the spacing between these fingers of fluid is about 5 centimeters. So to sort of try to get at this question of solifluction lobe formation, I'm going to ask a question, and rather than a formal hypothesis, you can think of this as kind of like an educated guess, right? We see these features, they look a whole lot like drips of fluid, like if you've ever seen those drip cakes that cost way too much money, or when you put oil in the pan and tilt it, you get these patterns. What I'm going to ask today is, are these just coincidentally similar because patterns are often non-unique? Or are there actual physical similarities between these systems that might help us understand how the incredibly complicated process of solifluction works? And so today I'm going to focus on, you can probably see in some of these images, there are multiple different patterns in these landscapes. There's sort of a downslope instability and a instability across the slope. Today I'm going to focus on the cross slope instability. So when I refer to wavelength, I'm basically talking about the spacing between two lobes. And I think this arrow is slightly misplaced, but if you look at the oil here where it's a little clearer, the wavelength would be the distance between the nose of one lobe to the nose of the adjacent lobe. So that's the pattern I'm going to focus on. So let's take a brief detour into fluids and what causes these patterns in typical fluid flows that you see, kind of on a daily basis. If you're like me, once you start thinking about this, you feel a little crazy because you're looking at the walls and noticing all the paint drips all over the place. They really are ubiquitous. So we have some understanding of how these patterns form in fluids, and at the simplest level, they form due to competition between gravity that pulls the fluid down slope or down the wall or down your cake, and cohesion in the form of surface tension that holds the fluid back. So in general, patterns form due to competition between different processes, and gravity and cohesion is competition between those is what causes these patterns. And so there's been a lot of work done to understand these patterns. But the basic idea is that when you have a front of fluid, so imagine you're painting a wall, the first part of the paint that's dripping down the wall, cohesion or surface tension allows the fluid to stall and thicken. So it's trying to hold it back. But in fluids, thicker flow moves faster. So there's sort of a nonlinear instability here. And then small perturbations across the front cause competition between these two effects and the formation of fingers that have a pretty set wavelength, as you can see in this drip cake here on the right. And so through experiments and stability analysis and numerical models, people have discovered that the wavelength of these fluid fingers goes as the thickness of the fluid and some kind of ratio between how fast it's moving and how strong the surface tension is. And so basically from this equation, what I want you to take away is that the wavelength increases with the thickness of the fluid and the surface tension, how cohesive it is, and it decreases with how fast the fluid is moving. And this has been shown, this relationship has been shown to be not extremely sensitive to the rheology of the fluid. So even non-Newtonian fluids have a very similar scaling to what's shown here. And so now I want to say, okay, since we kind of understand how these patterns form at fluid fronts, do we have the basic, at least qualitative ingredients to make a comparison between the cake icing drips and our solifluction lobes? So the first kind of key ingredient is that lobes do seem to generally form at terrace fronts. So if you're walking around in a landscape like this, there are terraces of soil known as solifluction terraces that can be anywhere from, a quarter of a meter to 2 meters high. So they're really noticeable sort of stair steps in the landscape. And often, sometimes those terraces don't really break into lobes. They have a fairly linear front, but then sometimes they do take on this crenulated lobate shape, which kind of hints at the idea that, this is some kind of actual instability in the landscape. There's something going on between this relatively linear terrace and this one that's breaking into lobes that's causing this instability. If we look further, if we zoom further into an individual lobe, we can see that solifluction lobes, here's an image in the upper left of a lobe, they have a very distinctive shape. So at the front, they have a pretty steep slope. It can actually be overhanging, so well past vertical. They're coated in a thick layer of tundra, usually, if they're vegetated lobes. Some of these solifluction lobes have large boulders at the front, and that's not the kind I'm focusing on, though all of this work probably relates to those two. They're known as stone-banked solifluction lobes. If you cut into one of these, which was probably easier to do in the 90s, to totally cut one in half, you can track the organic layer, that's this black layer here, and you can actually see that it goes underneath the front of the lobe. And people have carbon dated this stuff to see that it gets older and older as you go further back under the lobe. So this is showing us that these things are sort of tractor treading over themselves and very slowly rolling over at the front. If we look at how glycerin flows down a plane, you can see it has a similar shape. The scale here is much smaller. This is sort of centimeters scale, and this is meters. And at the front of the glycerin, the surface tension of the fluid and the force of gravity pulling it down causes this shape at the front where the flow kind of rolls over itself and you get this circulation at the front. So at least there's some kind of qualitative similarity between how these two different systems operate. Just for fun, here's a very high-tech video of vegetable glycerin flowing down a plane with a sprinkle as a tracer. So you can see the sprinkle goes over the top and the glycerin is sort of rolling over it. And I can never help but show this video. I don't know where this came from and why this happened, but someone put a can of Chef Boyardee in a lava flow, and it's just a very nice illustration of how this sort of rollover effect happens in fluids. So the problem here is that soil is not a viscous fluid, obviously, right? It's not, it may kind of act like that. We'll talk about that later, but we don't really know the rheology of soil. And clearly a granular material is a different thing from paint dripping down a wall. But some recent work, this is a relatively new area of study, but some work in the physics community has started to look at how granular materials can take on fluid-like instabilities. So in this paper, they poured what they thought was dry sand from a very high height, and they dropped a high-speed camera with the sand stream and caught it in like a pillow on the floor. And they saw that the sand breaks into droplets that are very similar to the droplets you see when you turn on your sink. It's called a Rayleigh plateau instability. And they actually found that humidity in the room that they didn't control for caused small capillary bridges between the grains that allowed them to form these droplets. So the cohesion between the grains acted like a surface tension kind of force and allowed the sand to form droplets that had a very similar scaling to those you'd see in your faucet. And in soil, at least one thing we have going for us is that there's no shortage of sources of cohesion. soil is very cohesive, as I'm sure we all know from experience. Microbes can add cohesion, permafrost and icy properties can add cohesion to the soil. Just the composition of the soil, if it has a lot of clays, can add cohesion. Vegetation and roots can really reinforce the soil. Boulders, may add cohesion, not in a direct way, but more of a sort of stalling of the soil kind of way, because they slow down the soil. And they, in this image, this is a stone banked solifluction lobe where the lighter colors are large boulders and the darker colors are soil. So you can see that boulders can cause sort of an organization, which is a whole other interesting instability, I would say. And then of course, soil moisture. If you've ever built a sand castle, you know that there's this sort of nonlinear relationship between water and sand, where if you have a little bit of water, the sand is very sticky and you can build a sand castle. But if you have too much water, it's saturated and it can't maintain its shape. So our sort of, again, educated guess idea could be that given the shape of these lobes, that they're much thicker at the front and can even roll over themselves. They have some kind of important cohesion, holding them together that may be concentrated at the front of the lobe. So similar to how surface tension is concentrated at the surface of a fluid, we have this guess that, given the shape of these lobes, maybe something similar is going on, but at a much larger scale. So there's really no or very limited data that we can use right now to try to understand these trends in cohesion across a lobe. But we can guess that maybe, often there's increased vegetation at the front of the lobe. You can see that in this image. That could cause increased cohesion at the front. You can get compression of the soil as the front is rolling over itself, which might, cause it to move more slowly up there. Perhaps the solifluction processes are not as efficient at the front because you're close to a, lateral boundary. Depending on the moisture content, if the front, has sort of an intermediate amount of soil moisture, you could have these capillary bridges that add cohesion. So, again, we don't really know, but just kind of based on these, on the information we have, these processes might be going on. And, this paper, which is amazing, from 1970, where they measured hundreds and hundreds of lobes in Niwot Ridge, Colorado. This is the only data I could find right now. I think there are some new exciting studies coming out that look at deformation patterns on a single lobe. But, in this paper, they just put like wooden stakes in the ground and measured the transport rates over several years. And you can see that the soil transport rates, these numbers are in centimeters per year, increase towards the front of the lobe. That makes sense because the front of the lobe is thicker. And so we'd expect, even though it's a soil and it's not a fluid, that a thicker amount of soil should generally move faster. But then it kind of shuts down right at the front of the lobe where it's steepest, right? And so if you're familiar with geomorphology and sort of our ideas of landscape evolution, it kind of seems wrong that the steepest part of the feature is moving the slowest, right? And so this is what really points towards the importance of these cohesion processes. Something is happening at this interface at the front of the lobe that's causing it to slow down. And we think that likely has something to do with cohesion. So given all these at least qualitative connections between the lobes and fluid instabilities at fluid fronts, we can come up with a conceptual model of how these things might form just in the most sort of basic analogy to fluid instabilities. First, we acknowledge that there's some kind of downslope instability that's leading to these organized terraces. And I don't have time to talk about what might cause this today. It's likely a related process, but we kind of have to accept that this is a very common feature in these landscapes where you get raised fronts of soil that are 1 to 2 meters. But because I'm focusing on the cross slope instability, we kind of zoom into one of these terrace fronts and we say, okay, similar to our paint drips, we imagine that There's cohesion at the front that's resisting soil motion, that's allowing the soil to maintain these really steep, tall, terrace fronts. We have the concept that thicker flow should move faster. So competition between these two things, just like in a fluid, should lead to an instability. And in contrast to a fluid, which is a very thin film where you can kind of ignore, large amounts of roughness in the fluid, in a soil where in nature it's messy, there's a lot of heterogeneity, you can have big bumps in the landscape. So we say, okay, if you have a bump, it would like to kind of diffuse out in, basically due to something like hydrostatic pressure. So if you have a bump at the front of the terrace, there's some lateral flow that's trying to smooth it out. And with those three ingredients, we kind of guessed that competition between these things should somehow determine the wavelength of these lobes. And so we define, our relevant parameters that we're predicting are important are the thickness of the soil, which helps determine how fast it's moving, the slope of the topography, which also goes into the velocity, the wavelength of the lobes, which is of course what we're interested in finding, and some kind of length scale gamma that we define as a characteristic length scale over which the cohesion changes. So, this is our idea that something about the dynamics, we don't know what it is yet. We don't have pretty much any data from the field, but, something about how these things work causes an increase in cohesion towards the front of the lobe. And that is what this length scale is giving. So in order to make sort of a theoretical, prediction of how these things work, it would be nice to know what the rheology of the soil is. And the bad news is that that is incredibly difficult, and we just don't really know. Frozen soil in general is difficult to understand. Frozen soil is, I'd say one of the most complex materials on Earth, because it's a granular material that's temporally changing. So part of the year it's frozen, part of the year it's thawed, everything in between. You have different grain sizes, you have cohesion. It's an incredibly complicated material to understand. And we compiled vertical velocity profiles from the literature. So people put, rods in the soil and you can see how they deform. And most of them sort of have a characteristic exponential kind of look to them, right? And this is common in granular materials. So in a fluid, I hope you can see my cursor, in a fluid, you'd expect a velocity profile to have the opposite sort of curvature. In granular materials, you see this shape. It's related to the fact that pressure is very important in how the soil moves at depth. But, the main thing here is that these velocity profiles show that this would be some kind of granular rheology. And if we could compare it to a fluid, it's definitely not just a Newtonian fluid like honey or something, right? If you kind of think about it as a fluid, the viscosity should increase with depth effectively. But we also have to be careful because this field data is taken over long periods of time. And these are not really velocity profiles, they're displacement profiles. So this is sort of another, difficulty in understanding the soil rheology, because these things are time integrated, right? The way these Arctic soils move is that the surface generally thaws first. So the surface of the soil experiences more motion, a longer time frame of motion than the soil at depth. So we also don't know if these are really representative of velocity profiles or displacement profiles. So what do we do when we have a problem that's so difficult like this? We're kind of going to, at first, just do the simplest thing we can think of and treat it as some sort of viscous fluid. Again, I want to be clear that we know it's more complicated than that. But right now, since we have very little information, we're going to do this as a first approach. And so we treat it as a laminar fluid. The one thing we do know is that soil will not be turbulent. So that's nice. And, you know, if you know something about fluids, this should look pretty familiar to you. We have a shear stress of the soil. It's basically due to the weight of the soil moving down slope. And then we allow for this hydrostatic pressure term. This is what lets the soil kind of, you know, try to smooth out the bumps that it has. Since we know that assuming a Newtonian fluid is not a great assumption, but we don't know what kind of non-Newtonian it would be like necessarily, we define some kind of bulk viscosity. So in the, you know, in the data I showed you before, the viscosity or the effective viscosity would be changing in the soil. So we're assuming there's some kind of bulk viscosity that we care about here. And, you know, at a later date, we might be able to know more about what that relationship would be. But the key here is that we allow the viscosity to change downslope. So it's not a constant, but it can actually change as you approach the front of the lobe. And again, the idea behind this is that cohesion is generally related to effective viscosity. So the more cohesive a material it is, the more effectively viscous it is. It kind of makes sense. So this is our way of trying to incorporate these ideas about changes in cohesion into a simple model that's based on a fluid. And so we do a scaling analysis where I don't have time to go into the details, but we non-dimensionalize this and try to predict what would the relationship be between different scales in the problem. And so we find that the wavelength, so again, that distance between the noses of the lobes, should increase with the thickness of the soil and this characteristic cohesion length scale gamma, and it should decrease with the slope of the soil, which represents something about the velocity to some power. And so this relationship is different, but actually quite similar to what we saw for the fluid drips, right? The power is slightly different. It was 1/3 for fluids. And instead of surface tension, we have this cohesion length scale instead. Here's a reminder of what the different parameters are. We have the thickness and the slope. Sorry, this should be phi, not theta, to match this figure, the cohesion length scale and the wavelength of the lobes. And so we have this sort of, you know, first guess theoretical prediction, kind of assuming that these things act similarly to a fluid instability. So what we did was use a wealth of remote sensing data that's available from Norway. They have LiDAR, sub-meter LiDAR of the whole country that's freely available, which is amazing. And so this data collection and data set analysis was really spearheaded by Mulu Fratkin, who was a postmaster's student at Los Alamos. And basically, along with a post-baccalaureate student and Joel Rowland, who's a scientist there, we had a lobathon where we measured a lot of these solifluction lobes from imagery. And so we had about 30 different sites across Norway. And this is an example of what the LiDAR looks like in the upper right here. And so we did a semi-automated analysis of basically the wavelength of the lobes, their height, and the topographic slope. We have no control, of course, over this cohesion length scale, but we stuck with things we could measure. Here's an example of the beautiful topographic profile. So you can see there's a sort of a train of lobes here, and we could get the planform wavelength from the imagery. And then using the DEM, we were able to get the height at the very front of the lobe. And we measured about 3,500 of these. You know, you might be wondering why we didn't use some sort of machine learning only approach. There are some reasons for that. It's incredibly difficult actually to pick these out. They're not the most obvious pattern. You know, they're fairly variable between field sites. And even though this seems really tedious, like the students were tortured, it only took us 2 days to measure all these. So it's really not bad using this sort of semi-automated approach. We found that the wavelengths of these lobes, you know, are consistent with other studies on Earth. And again, consistent with those studies, we see that lobes on Mars that people see are a bit larger than the ones we see on Earth. But the main thing we were interested in was to see, okay, does our first effort theoretical model in any way describe this data? So let me walk you through this plot. We have the wavelength of the lobes on the y-axis and the height over the topographic slope on the x-axis. So this is our theoretical prediction. We would expect that the wavelength should increase with this ratio of height over slope to some power, right? So because we have so much data and there's a lot of scatter, I made this is a density plot. So the colors of the hexagons show you how many data points are in each sort of spot so that you can actually see. You can see there's a lot of scatter. These are taken from the whole country of Norway, different climates, different rock types that we have no constraints on. But if we bin the data, so just, first effort trying to look through the noise here, right? If we bin the data, we see that there is a clear increase in wavelength with this height over slope term. And if we put our theoretical prediction on the points, again, we're not fitting the data in any way. This is just a line with a half power, right? Like our theoretical prediction. You can see it doesn't do a bad job. Our theoretical work actually predicts pretty well sort of the mean behavior of wavelength with these parameters that we've identified as being important. So that's pretty interesting, right? Because this shows you that, yes, nature is incredibly messy and there's clearly other stuff going on, other parameters that we're not controlling for that contribute to the spread of this data. But when we sort of squint our eyes and look in an average sense, the trend between the wavelength and these parameters really kind of fits with our first effort theoretical model, indicating that maybe these things are actually quantitatively behaving like a fluid instability. So that's all good and really interesting, but I would be remiss to say that's the end of the story. There's a lot of scatter in this plot. We only see these things in cold places. So what about climate? None of the fluid analysis has anything to do with climate, right? We're just assuming that the soil is sticky and moving down slope. That has nothing to do with freeze thaw. So we did also look, they have an incredible climate data set in Norway. I think every 30 minutes for the last 50 years, all over the country, which is amazing. So we used an interpolated climate data set from the various stations they have to compare with our data. And first, we just looked at elevation, just as a first effort. We looked at the thickness of the lobes and their wavelength, and we do see a clear increase in lobe size with elevation, which points toward a climate control on these patterns. So what might be happening there? Well, we do know something about ice lensing and frost heave, and some really good modeling and theoretical papers have shown that this ice lens formation occurs under pretty specific temperature and moisture conditions. And in general, it's complicated, but the formation of these ice lenses is most efficient when the temperature amplitude is high. So when you have a lot of cycles over the freezing window, and when the mean annual temperature is lower. So it needs to be cold enough to form these. And so when we look at our data, here are the plots of lobe height and wavelength with elevation. And then on the right here, we have the temperature amplitude in degrees C. So this is the mean annual temperature amplitude. And then the colors of the points are the mean annual temperature by itself. You can see that the relationship is messy, but there is a general increase perhaps in lobe size with temperature amplitude. And there also is a general increase as you decrease the mean annual temperature. The points get bluer as you move to larger values of height and wavelength. So one idea is that, if these features are behaving like a fluid instability, perhaps the way the climate controls them is through the lobe height or through the thickness of the active layer. And, similar to fluids, the thickness of the flow is a very important property for the patterns that you see and the wavelengths that you see. It's probably the most important pattern or aspect of the pattern. So one idea is that, even if the physical explanation for these patterns doesn't necessarily rely on, Arctic processes specifically, the fact that we have those processes going on and really poofing up the soil in a way that doesn't happen in temperate places can enhance these instabilities. So basically you have frost heave. I live in Rochester now, and we couldn't get the door open to the garage because in the winter, because there was so much frost heave here. We're not even in the Arctic. It really, seriously heaves the soil. So maybe the efficiency of that process gives you enough thickness of soil that's moving throughout the year to really impact the morphology of these features and help them form. But we need much more data to actually say that with certainty. So one thing we'd like to do is conduct physical experiments where we build a model hill slope in a climate chamber. This is in our lab. And we can control the temperature cycling with high accuracy. We can also control the humidity to some extent. And basically we would like to look at, how do different temperature cycling regimes, both absolute range and frequency, how does that affect the efficiency of frost heave? Because there hasn't really been much work done on that, and that might give us some predictive capabilities to understand, how we expect the climate to affect frost heave and therefore solifluction lobes. The other thing we plan to do with these experiments is you can walk in here and it's big enough to do a few at one time. So we'd like to look at different types of soil under the same temperature conditions and compare how frost heave changes. What happens when we change the percent silt or clay in the soil, for example. So the takeaways from this part of the talk are, even these really complicated, super slow moving materials seem to be producing patterns that really look like fluids, but over very long time scales and much larger length scales. This is really interesting because, we're connecting two very different systems that seem to be behaving in a similar way that, but in a parameter space that hasn't been explored in the lab or in, the fluid world. The other interesting takeaway is that cohesion may not just slow down soil, which is sort of our traditional formulation of what it does, but it may contribute to these large scale instabilities that might even speed up soil. There's these nonlinear effects. So it's showing that cohesion might be even more important in landscape evolution than we currently think. Another key point is that, there's really complicated rheology of these soils, and it would be worth trying to understand it better because we really don't have a good model of how these work. But these soils may be examples of new patterns that are sort of on the edges of our understanding of these more classic systems in fluid and granular mechanics. And then climate does have some effect on the morphology, maybe through initiation of the instabilities and formation of the active layer. If you're interested in more info on this work, you can check out our paper that came out last year. And sort of more next steps that we've been trying to, take are field work. So I talked about a lot of educated guesses, maybe just guesses in this talk. And it would be really nice to have more field data that's sort of targeted to these questions. So we got to go to a field site near Nome, Alaska this summer. We met up with some collaborators from Los Alamos National Lab and Dartmouth, and we did some measurements of solifluction lobes. We just got to see them in the field. Here is the front of a lobe that had recently failed. And you can see that there's certainly a clear difference between the organic layer on the top, these roots really holding the soil, and this silty layer underneath. So we're really interested in what the differences in mechanical properties are of the surface layer of the soil and the stuff underneath, or the front of the lobe and the part of the lobe further upslope, because from our theoretical analysis, we would predict that there's some kind of fundamental difference between the different spatial aspects of the lobes. So in this picture, the grad students in our lab, John Paul Slayman and Nasare Mohammed Samasi, are putting a bolt in the ground. We're trying to do some displacement measurements, trying to recreate that picture I showed you from 1970, where we look at displacement across a single lobe to characterize how the soil is moving. And we also collected samples to look at changes in cohesion and grain size and geotechnical properties across the lobe. If you're interested in more work at this field site, particularly the group out of Los Alamos and Dartmouth have been doing a lot of cool work to characterize soil failures and solifluction and motions on the Seward Peninsula in Alaska. So this paper is up for discussion on eSurf if you want to check it out. So in the last few minutes, I'd like to, we were kind of stuck on Earth for the first part of the talk, and I hope I convinced you that, we've at least made some amount of progress trying to understand how solifluction lobes form, and, at least some interesting ideas or hypotheses that maybe they act like fluid instabilities, but there's still a role of climate. And of course, anytime you talk about climate and patterns that you see on Mars, there's some really interesting implications there, right? So this image on the left again shows these lobate features on Mars. The image on the right here is in Alaska. And so some recent work has characterized these lobes on Mars to try to understand if they are indeed like solifluction lobes on Earth and what that means about the past or even present climate on Mars. So this really interesting paper came out in 2020 where they measured a lot of these lobes on Mars, measured some lobes on Earth, and they also looked at some patterns in the desert known as zebra stripes that look sort of similar but are not associated with frost heave processes. And so they found, they really looked at the plan form morphology of these lobes, so the aspect ratio of the length to the width. And they found that at least the Martian lobes occupy kind of a similar parameter space to those on Earth. They tend to be a bit bigger, but there's also plenty of overlap in their size. And they're not quite as similar to these non-frost heave patterns that you see in the desert. They found that the lobes on Mars tend to occur on steeper slopes, which we don't totally understand why. It might be due to differences in material properties. And they acknowledge there's possible climate implications to the idea that these things are similar to solifluction lobes, but there are also other processes that might form lobes like CO2 sublimation or other things that might be happening on Mars. But then some other recent papers have shown that maybe these lobes are actually active. So the typical idea is that they're relict on Mars. They represent past climate that may have been icier and caused more active soil processes. But some imagery analysis has shown that at least some of the boulders that you can see in these images are moving at fast enough rates to actually measure, from differencing images a few years apart. And that would indicate that some of these features are moving without liquid water and they're currently active. So this calls into question the idea that we need frost heave and thaw processes for these to move on Mars. So my grad student, John Paul Slayman, is doing this project. He's a second-year PhD student, and he's been working on trying to quantify the lobe morphology on Mars and compare to Earth now that we know something about what the three-dimensional scaling should be of these lobes. So we use the same method on Mars here to measure both the planform wavelength of these lobes and their height and the topographic slope. And so these are in crater walls, right? We use high-rise imagery, which is really high resolution. And we can pick out these lobes. I think we looked at 7 craters so far. And here's an example of a good topographic profile that we can get. So in the past, people have only looked at the planform morphology because some of the digital elevation models are not high enough quality to see the subtle solifluction lobes. So we've been using some maps of DEM quality to basically pick out which lobes and which craters we can trust the data enough to get lobe heights, because we know from our scaling analysis that that's actually the most important parameter. And so here's an example. You can see very subtle, these craters are steep, so the lobes don't stand out that much. But if we detrend the profile, you can see, fairly clearly, here's 2 lobes kind of going down slope. We can get what their height is at the front of the lobe and make our plot. So again, this is preliminary data. We've only measured about 200 of these things. But in the background here in green, I've gotten rid of the density plot because it would be too crazy. Now I just made the Earth data green, so that's in the background. The stars represent Mars, our Martian data, and we normalize the data by just the mean wavelength on each planet and the height and the topographic slope. So just what is the mean wavelength we saw in all the Norway data, and what is the mean we saw on Mars? And you can see first that it's interesting, the Martian data falls right on top of this noisy cloud of data from Earth. It has a similar amount of scatter, but it really does fall right on top of it. So this scaling between the wavelength and the height and the slope seems to follow a similar trend. If we bin our data in the same way that we did for Earth, that's the black stars, and we look at our theoretical scaling, you can see that the sort of average trend again on Mars really follows the same half power scaling, which is pretty interesting. And we're actively trying to improve our data collection of the lobes and make it even more reproducible, and make sure that we're really doing a good job measuring these. But this preliminary data shows that there's something to be said that these lobes are actually maybe physically similar to what we see on Earth, which is really very interesting. And so, in the title of this talk, I think it's something about a secret recipe. I would say we have not yet found the secret recipe for these complicated features, but we're making progress. And what we need to know is whether or not water and ice are actually needed for these to form. So we see them in cold places on Earth, which points toward the importance of frost heave processes. But the fact that we also see them on Mars and they might be actively moving, and the fact that they're similar to fluid instabilities, which just require sticky soil that's moving down slope, kind of calls into question the absolute necessity for frost heave. So we really need to try to get at that question to be able to confidently say something about climate on Mars. We need to understand what the cohesion trends are in the soil and what actually causes these to form. Is there a critical velocity? Is there a critical thickness of the soil that you need these to form? So even further future steps, would be kind of risky but exciting experiments where we try to make a lobe in the lab without any water and without any frost heave in a granular material at slow speeds. And so the idea would be to use some kind of cohesive sand, like this kinetic sand, which is really fun to play with. Maybe put it in a very slowly rotating drum that would have to be pretty big in order to form solifluction lobes, and basically do the null experiment of can we form these without frost heave processes and without liquid water? And this would really help us understand Mars better. And finally, I just want to end with just in closing, you know, this work has been incredibly humbling and interesting to me. And I think it's really cool because these landscape features that are kind of, you know, humble themselves, they're rather subdued in the landscape. They're not, you know, they're a couple meters in height, tens of meters in wavelength. They have all these connections to totally different fields and systems. You know, you can go a little crazy reading these papers and fluid mechanics and buckling and wrinkling of solid materials like pumpkins, and deformation of amorphous solids and roll waves and cornstarch. And you can really make all these connections between these different fields. But the key is that even though these other studies can inform our understanding of landscapes, because the landscapes are at such different scales and they're messy and there's a lot of heterogeneity, you know, we can't just take stuff from these other papers directly. We have to kind of do it this back and forth of understanding how are these systems similar, but also how are they different. And I think that's really interesting to me. So with that, I'll end and take any questions.
Thank you so much, Rachel. So for the questions, Kevin and I will go back and forth of reading questions that are queued up in the chat. Maybe I'll just start with Tyler's and then Kevin can ask his question himself. And feel free to keep sending in your questions. Trying to get through them all. So I'll start with Tyler's question. He says, so cool, Rachel. If lobe size reflects climate in some way, what's a guess for how long it takes to adjust to new conditions? Decades, centuries?
That's a really great question. So just kind of, you know, thinking about it on the fly, I would guess that once a lobe forms, it's difficult for it to change its size. And the only thing that could happen is you might form new lobes at the front of a lobe. So for example, I don't know if this is the best picture. Actually on Mars, you can see this. There's some larger scale lobate features. And then at the front of some of those, they break into smaller features. And so I would imagine the time scale for that adjustment would be on order of the time scale to form a lobe in general, which we have no idea what that is. If I were just really going to guess here, I would say hundreds of years, but we really have no data on that. I think it's an interesting question. And this is also a good time to point out that our scaling analysis would really only predict the initial formation of lobes. So it doesn't predict any of these nonlinear later stages of lobe formation. So I think with climate change, you know, you might break into some of these smaller ones at the front as sort of secondary instabilities.
Great. Okay, I'll let Kevin read his question.
Yeah, Rachel, I was thinking about the gamma factor and if you've thought about what really goes into that, because in particular, it's pretty surprising that between Mars and Earth, it seems like the gamma is similar. And, you know, surface tension of a fluid between Mars and Earth would be very different and so on. So have you thought about like modeling that in terms of some granular properties or?
Yeah, that's a great question. You know, that's certainly the most uncertain aspect of this. And I will point out that it's not related to the actual surface tension of the fluid and the material. It's more of an abstract idea that the bulk cohesion or the effective viscosity of the material is changing towards the front. So I would imagine that the length scale is similar between Mars and Earth because it's probably related to the size of the lobes. You know, if in my extremely primitive, hold on, sorry, non-technical drawing of a lobe here, for example, I might imagine the length scale to be related to, you know, the length over which the bump at the front of the lobe exists. And I did try to look in some imagery and it seems to be like a meter. So given that the lobes on Mars are not too dissimilar from the size on Earth, you might imagine a similar length. But we really need to do field work and have a better idea of the rheology of the soil to get at that question.
Yeah. And is it somehow related to like a contact angle idea? Is that what I can understand from that?
Yeah, kind of. Yeah, I didn't have time to talk about that today, but you do see that the angle at the front of the lobe kind of changes depending on these parameters too, which is similar again to a surface tension fluid. So again, I would guess that length scale is somewhat consistent and based on the size of your lobes.
Yeah. So Nicole's asking if lobes don't need water, but lobes need cohesion, where does the cohesion come from on Mars? And he thinks it's aliens. It's possible.
Well, yeah, that's always the answer. That's a good question. And we know that there is cohesion on Mars. So there are these cool papers where the rover rolls over some soil, takes a picture of its tire tread marks, and people have tried to quantify the cohesion that way. I'm not totally sure what the current ideas are, but there are salts that could lend cohesion to the soil. There are possible, smaller scale like electrochemical clay kind of processes, but I don't really know. But it's clear that there is cohesion on Mars.
Well, I'll ask Eaton's question, and it's related to the first question we had from Tyler. Asking if you have a sense of the longevity of the lobes once they stop being active, what degree the morphologies we see today on Earth or Mars reflect past rather current conditions?
Yeah, that's an excellent question. I wish I had a better answer. Obviously these things would sort of diffuse over time if they stop being active. And so we do see relict lobes, particularly in Pennsylvania, and in other places that are now more temperate, and those are much more subdued. You would not see them sort of sticking out 2 meters above the surrounding topography. So in terms of quantifying that, people have done some dating of lobes to see how old they are. And they've even seen at the same field site, one looks like it's been inactive for 10,000 years and another one is active now. So it's a very difficult question, but it's absolutely important for understanding how these work. And again, one of the assumptions in our climate data comparison is that these lobes are active in Norway. And so therefore the current climate conditions have some reflection in the current morphology. And, I think that's a pretty good assumption because we know a lot of lobes are active in Norway, but that's not necessarily true all over the Earth.
Kevin,
Cool.
You have Ellen's question?
Yeah, so Ellen has asked, have you used spectral analysis to look for wavelengths in the lobes? So are they periodic?
Yeah, so Mulu, who found this incredible data set, spent a long time doing some spectral analysis of the imagery in Norway with varying success. It turned out to be pretty difficult to pick out the lobes because there are so many other patterns in paraglacial landscapes, and because the sort of qualitative look of the lobes is different at each field site. The actual shape and what they look like is actually pretty different. So he wasn't able to have a clear answer, but I think that would be a really important study to do in the future to characterize, since we have sort of different stages of lobe formation and our scaling analysis is sort of stuck with this initial what is the initial wavelength, spectral analysis would help us understand the distribution of wavelengths. So I think that's a good future project.
Great. I think we've asked all of our questions in the chat. Feel free to keep, well, I guess we're at 11 or 11 my time. Do we have any more questions from the audience? Feel free to also raise your hand if you'd rather unmute and ask your question. Doesn't
Cool.
seem like we have any.
Looks like we're good.
Yeah, I'll go ahead and ask the audience to Zoom clap or unmute if you'd like, and thank Rachel for such a great talk.
Yeah,
Thank
thanks,
you.
Rachel. That was really
Thank
good.
you. Thanks for having me. It was great.
And so thank you everyone for coming. Thank you, Rachel, for the talk. And look out for the next talk, which is in November. That's from Dr. Ann Jefferson of Kent State University. Hope to see you all there.
Yeah.
Great.
Thanks, everyone.
everyone.
Jimmy, do we end the recording?
I
or
can
do
go ahead.
you-
Yeah, I can end it. Yeah.
Okay.
Awesome.
Yeah, nice.
That's great. Cool.